skate for an hour and a half, I'm going to be sunburned. But no, I feel much better than I did yesterday. Yesterday was rough. My tongue was going numb. My mouth was going numb. It's not COVID. Those are not symptoms. It's apparently a very common symptom, though, of the Osage orange, the horse apple tree. No, not chicken pox. I had chicken pox when I was like 8. Do what? You found horse apples that were actually formed? Yeah. They're normally like August-ish is normally when you find them everywhere. I was going to say there would have been babies, but this is trash. I'm sorry. I'm trying even just in a few minutes. I've had all different kinds of emails show up. Okay, so this is going to be fun. I have not done thermo in, I have not done thermo in literally a decade. And like I said, I meant to sort of refresh myself again during the last period of off. So, if for some reason, as I go through this, and a lot of this, I can't run my smartboard. I hate this thing. We do have a work day tomorrow. If for some reason I do tell you guys something that's incorrect, I will fix it. You guys are getting the first, because originally this was a staple packet. So today, I reprinted it. So as long as you pulled the right thing, it's just this page. And then tomorrow is making sure that we can understand how to read these puppies. In fact, I'm going to go get my key. Like I said, it's been, it's the same. It's the first page. You guys don't have a stapled one. How did you get a stapled one? No, that's the notes. The assignment should not be. The notes are stapled because the original. This is the original assignment from the trash. Because tomorrow is making sure that you understand how to read one of these diagrams properly. And then we're going to do, my nose still itches so bad. We're going to do calorimetry. Today's Tuesday? Thursday. And then I've got a Google slide making sure you understand calorimetry Friday. We are like a day behind the other chemistry people, but I'm not worried about it because we've got how many weeks left of school? If you count the full week. So for today's opener, oh great, my coworkers are texting me now. What? Oh, okay. We have two different prefixes that we're going to talk about with a chemical reaction today. There are endothermic and there are exothermic reactions. Do you know what the prefix endo versus exo mean? Because they're opposites. Exo means exit, out. So what does endo mean? Enter. Perfect. That's exactly what they mean. So we're trying to figure out if our heat, what forces the reaction to happen. Why do the product or reactants create the products? Does it need to bring heat in to make it happen? And I know they can't see me pointing on the screen. Or does it need to give heat off to make the reaction happen? And like I said, these curves, it's been a very long time since I've looked at them. So I just yanked my key to help for a minute. Is it frozen? Oh, it's frozen. Sorry, it's frozen. Oh, it's not animated. No. Let me fix it. This is what I get for getting a phone call last second saying, come pick up your kitty cat. Although it was in a very cute box. I know that sounds so messed up, but let me animate all of these puppies real quick. I wish I could draw on my smartboard. I may have to redraw the curve on the dry erase I'm so sorry. I should have done this over the weekend and I ran out of time. There we go. All right, so we are doing something called enthalpy. Enthalpy is a fancy science word that just means heat. That's all it means. Does the reaction absorb heat? And it's going to feel cold to your hands. I'm sure you guys have all snapped a light stick before. When you shake it up and it glows. It's cold to the touch. That's an endothermic reaction. It needs to bring heat in from the outside. And so therefore to your hands, it's going to feel cold. Whereas exothermic is going to give heat off. And to your fingertips, it's going to feel hot. For what's on your first page, your first part, a reaction rate is how quickly do reactants become products. That's all it is. And there's things we can do to speed it up. We don't always use catalysts. But in order for your reactants to become products, they have to slam into each other with quite a bit of force. And today is Star Wars Day. It's May the 4th. So go figure. But you're not going to convert. The reaction's actually not going to happen unless you have enough interactions of the particles with enough force to actually make those products happen. And with these, you're going to have this weird hump, and that's what forces the reaction to happen. It won't happen. It won't happen here. It won't happen here. It won't happen here. It'll happen here. And it's a matter of understanding how to read one of these diagrams. How much potential energy do the reactants have? How much do the products have? How much was necessary to force it to happen, which is always greater? How much heat exchange occurred? It's not a hard thing to read. It's just having to understand where do you take your measurements from when it, because you guys don't have this page, when it comes to one of these diagrams. Where are you yanking the data off? And honestly, some of your reading graph skills, for whatever reason, are lacking, and I get to try to fix it today. Your reactants, your reactant particles have to slam into each other. And they have to do it with enough force, where are my matches at? Enough force and energy. Here we go. I'm going to set off the fire alarm. You have to do it with enough force to make the reaction happen, or it ain't going to happen. It's just going to sit there, and your reactants are just going to stare at each other, and nothing's going to happen. There will be no products. When it hits that threshold, then the bonds break. And ignore this is actually, believe it or not, this is actually Earth space on the board. We're doing chemistry right now in Earth space. I don't think they like it very much. But in order to, so like this thing that's on the board, which y'all can't see it online, this is glucose. This is what it looks like on a structural level. For us, when we eat things to get the energy out, we need to break bonds. And unless you have enough force or energy to do it, it isn't going to break, because we do the opposite of this. And y'all had biology last year, but that was COVID, right? Right? Do you remember doing photosynthesis? Okay. We do the opposite of this. We take food, sugar, and we use oxygen to break it down and produce water, i.e. pee, and we breathe out carbon dioxide. This direction is what plants do. We literally break these bonds, and that's what gives us our energy. So I'm actually glad I drew glucose on the board. I had to look it up. It's been a long time since I've done biochem. If they don't hit the right way, nothing's going to happen. Things that affect how fast this occurs. How hot is it? Heat will accelerate, whether it's the presence of or the absence of. Heat will accelerate this process. Normally, it's an increase in heat. Okay? When a gas is hotter, it's more agitated. It's moving faster, and therefore it's slamming into each other faster. Depends on how concentrated it is. If you've got more stuff, they're going to slam into each other faster. Depends on how big it is. Bigger things hit more often, smaller things hit less often. A lot of this is sort of like, duh, that makes sense. You've just never been exposed to this before. When we change particle size, when we increase when you crush something, you expose more of the outside of the smaller particles. Think of a sugar cube, and I know I've used this before. A sugar cube, it's about a centimeter cube. If you throw that in water, it's going to take a lot longer than if you smash it up and throw it in water. It's still the same stuff. And then we can force things to happen faster using something called a catalyst. It just accelerates the change from a reactant to a product. We don't always use catalysts. Oh, and if I didn't mention, if you were not here yesterday, you missed a test. I believe it's still open in Canvas, but I'll have to double check. Now, in a potential energy diagram, whether it's endothermic or exothermic, you're going to see this pump, and you literally have to get over the hill before you make products. Until you bridge this gap, which it's your activation energy, you're not making any products. You've got to get over that hump in one of these diagrams. Like I said, if I mess up going over this next bit, I will fix it tomorrow. It's been a very long time. In order to change from a reactant to a product, it's going to take heat. It might bring in heat, like the light sticks. It might give off heat, like combustion, and burn something. But the measure of the change in heat is called enthalpy. And I honestly don't know why it's an H, but it is. Well, for heat. But your heat of your reaction can be positive or negative. Did it need to bring heat in, or did it give heat off? And if it has to bring heat in, it's endothermic. Endo means into. Exo means out of. And with endothermic, you need to, I hate using the words like container and system, but that's the way it is. You're taking the heat from the environment and pulling it inside the reaction in order to change from a reactant to a product. Exothermic, on the other hand, you have to release heat to the environment to change it from a reactant to a product. You still have a hump, okay, but this has the bigger hill and this has the smaller hill to start. If you're looking at it, and I know I haven't shown you the diagrams yet, I just really wish I could write on my board. I would try, but I know better. Especially since I don't even see the smart, the little, oh no, there is one over here. I can try. I guarantee you it's not going to work. I haven't tried to write on the board now in months. So endothermic feels cold to the touch. Exothermic feels hot to the touch. It just depends on which way the heat is flowing. Is it flowing into the system or is it flowing out of the system? Oh, here comes the fun part. Think I can write on the board?
Nope.
Probably not. Now these, I can try, but I guarantee you it's not going to work. I don't know where it's going to write. Probably on the Google Meet, but I can try. Okay, so we have endothermic, which has the bigger hill to climb before it makes products. And then we have exothermic, which has the smaller hill to climb before it makes products, but they still have a hill to climb. Oh goodness, this is not right. Let's see. We've got, let me make sure I'm telling you this right way, because I already made a key. Because like I said, this has been over a decade since I've taught this. Your heat, your potential energy of your react, think it's gonna work? Let's see. Except it's not calibrated. Oh my gosh, it worked for a change. I can't believe it actually functioned. Okay, let's try this again. Let's erase this.
Hey, I thought erasers was supposed to erase.
I know erasers are supposed to erase. Oh, no. Let me write.
Why it has to be
I knew this was going to happen. Okay, let's try it again. I'm going to try it again. All right, so you've got a couple of different things on here, and we'll come back and fill this in. You've got essentially 0 here. Okay, let's say this is 10. Okay, and let's say this is 50. It doesn't matter. I'm just pulling numbers out of thin air. Your potential energy of your reactants, because you have to be able to identify these things, is going to be from 0 up to its line. So in this case, my potential energy of my reactants is going to equal to 10 kilojoules. Okay. We also have a potential energy of our products. So that's going to be from here down to here. So that would be what? 40-ish? I'm estimating here. So my potential energy of my products is going to be equal to 40 kilojoules. It doesn't matter if you're endothermic or exothermic. In order for me to be able to change from whatever the snot I'm starting with to my products, I have to hit the top of this hump. And so from here to the bottom, which in this case is 50. So my potential energy of my activated complex is going to, I'm going to put it down under here, is going to be equal to 50. So these are all of your potential energies. Your change in heat, your enthalpy, your delta, which is the triangle H, is the difference between your reactants and your products. So my heat of reaction, or my enthalpy, which is the same thing, would be 40 minus 10. So this would equal to 30 kilojoules. What am I forgetting to put on here? I'm forgetting to put something on here. Oh, your activation energy. Okay, so what makes my reactants, let me change my color, because otherwise everything's gonna look the same. What makes my reactants change to my products, I have to hit this hill. And so that's gonna be from 50 down to 10. So my EA, or activation energy, is going to be 50 minus 10, which is 40 kilojoules. Now what am I forgetting to do? I said this has been eons since I've done this. I don't think I'm forgetting anything. Let me look at my key and make sure I'm not forgetting one. Potential energy reactants, potential energy products, potential energy of the activated complex, heat of reaction, and okay, no, I got everything on here. You have to be able to pull these numbers off of this diagram. Okay. Well, I mean, the paper that you guys are getting tomorrow is going to be analyzing these graphs, and it's going to ask you What is the potential energy of the reactants, the potential energy of the products, the potential energy of the activated complex? It's going to ask you your enthalpy or your heat of reaction, and it's also going to ask you your activation energy. Now, once again, we're mixing our chemicals together at the start, and I'm so sorry, those of you that are remote, you can't see how I'm pointing on the screen. You're not making products until you cross this part. This is your activated complex is a very, very unstable thing that's happening. This is where we are literally switching from what we're starting from to what we're changing into. But you can't do this until you've reached what's called your activation energy. So wherever your reactant started from to the top of that hump. Now it's the same. I can't believe I can write on my board. Okay, so it's going to be the same thing over here on the right. Use a different color. What is this? What the heck just happened? I don't know. Somehow I hit something with my pinky. I don't know.
Are you trying to like
No, it's like I don't know.
Microsoft
I opened something. This is a school computer. Are you joking me? All right, so you're in this case. This is exothermic. Endothermic, like I said, has the bigger, like, roller coaster hill at the front. And your exothermic has your bigger roller coaster off the backside, if you will, if that helps you understand. You're still going to have a potential energy for your reactants. So let's see, we said this was 50, this was 10, and this was 0. So your potential, there's like a chip in my board. Okay. Of your reactants would equal to 50. Your potential energy for your products would be, what do you think that is, 30? What do y'all think? You think it's 20?
We're looking at like 20.
20? Okay, so we'll say that's 10 kilojoules. Your potential energy of this magic thing that lets the reaction happen, your activated complex. So your PEA would be, so this would, let's say this is 60. So that would be 60. Let me change my colors here. I'm sorry if anybody's colorblind. I'm not trying to pick on you, I promise. Your change in heat, so we said this was what, 20? This would be 30 kilojoules. What am I forgetting? Potential energy, reactants, products, activated complex. Oh, so then your activation energy, 60 minus 50, would be 10 kilojoules. If you're having to put energy into the system, your delta H is positive. It needs to gain energy to force it to work. If you're exothermic, then you're giving off energy in order to make it work. And that's going to be a negative heat. I remember when I was your age, this was confusing as snot. That's why we have a workbook. I'm just glad I could write on my board for a change. It's never going to happen again, ever. No, well, I can try. You want me to try erasing it again? You think it'll work? Here, hold on.
Yes.
I yield. I give up. I swear. All right, so we're gonna do clear ink. At least I can do it that way. So if I use the matches, no. Let you play with fire, you might burn each other.
Yeah.
Okay, so we know when I light the match, does it give off heat or does it absorb heat?
Gives off.
Okay, so it's endothermic, right? Or is it exothermic? It's exo. Okay, so I still have to accomplish this. So if I do this for 5,000 years, is it going to light the match?
No.
No. If I do this, 5,000 years, it's going to light the match.
No.
If I do that for 5,000 years, it's going to light the match.
No,
Why? What am I not doing right?
there's not enough friction.
So if I do that, it does light the match. Okay, and that, please don't set off the smoke alarm. That is activation energy.
Oh, so wait a minute. Is that
I gotta have one in here somewhere.
why I've been smelling matches all day?
I don't
I've been
possibly
smelling
either
that.
that or yesterday because we are literally a day behind the other teachers. But a match is a great example of you have to, whether it's this way or this way, you have to have enough energy to be able to get, it's back there, so I think I'm, God, it's stink. You have to have enough energy, enough friction, enough force. It just so happens to be Star Wars Day. Coincidence. Woo, woo, that's stinky. That's sulfur for you. But really, a matchbox is a great example. And like I said, I'm sorry those of you remote that couldn't see what I was doing with matches. Why are you not going forward? Why are you not going forward? Oh, there we go. I was pushing the wrong button. So it doesn't matter which of the two, you've got that hump that you've got to overcome to be able to switch from starting to ending substances. That is called activation energy. We abbreviate energy as a capital E, both in chemistry and in physics. I miss teaching physics. It's my favorite one to teach. But if you don't overcome this weird like limbo place, it's not gonna happen. Like I said, I can tap a match on this for 5,000 years and it's not gonna light. Or I can slowly move it and it's not gonna light. You've got to have enough force and you've got to have enough friction to be able to start the chemical reaction. And in this case, it's combustion. I honestly don't know what's in the striker in this. I've never looked that up before. Like the part that's rough that you strike a match on. To do endothermic, your roller coaster up is much higher. Exothermic, your roller coaster down is much larger. And like I said, the activated complex, the no man's land, the thing you have to overcome is just how we switch. You're not going to switch if you don't cross that barrier. This is one of the few times I wish I actually activated my camera, but my camera to here does not match. All right, enthalpy of reaction, delta H. Once again, the triangle means change in. That's a physics thing too, if you guys take physics. I miss physics. If it's exothermic, it releases energy, which is why it is a negative value. If it's endothermic, it has to absorb energy. It must bring in heat, so it is a positive value. Which I think most of this is on your thing. If I didn't blue it out, I do apologize. Had a rough couple weeks. But this heat of reaction it's what's necessary to force a reaction to occur. Did you guys have to write anything down for this one?
No.
No. Okay, good. I don't have them in front of me. So exothermic, a negative enthalpy or heat of reaction. You are releasing energy. When you see one of these, your heat, that should be a capital K. That is, I took it straight off the notes. I'll fix it. So it's going to release 393.5 kilojoules of energy. So my delta H is negative 393.5 kilojoules. That really should be a capital K, but it's not a huge deal. However, if it's endothermic, since it absorbs the heat, your delta H, your kilojoules, are going to be on the reactant side. And it must obtain, in this case, this is when calcium carbonate breaks down to make calcium oxide and carbon dioxide gas. Oh, awesome. I'm doing this in our space right now too. So you have something called limestone, a type of rock, requires energy, breaks down to make calcium oxide and releases carbon dioxide gas. We are literally doing global warming right now in my Earth space, which is why all of this biochem and this chem is up on the screen. Like I said, this is not you guys. This is Earth space. So exothermic will have it's on the right. If I ask you the delta H, you need to make sure you put a negative or it's wrong. Endothermic, your heat is on the left. It should be a positive. Honestly, if you don't put a sign in front of the number, we always assume that it's a positive. Let's see where we're at. It's been so long since I've done that. Oh, we're going to analyze one. These types of equations are called okay, so this is thermodynamics. Thermodynamics is actually way more complex than this. We're just sort of scratching the surface. If y'all go off to do chemistry, this will get much more complex. But most of you won't. And so we're just, like I said, we're just sort of scratching the surface. It's just, do you release, which is exo, or do you absorb, which is endo? All right, we're going to analyze this thing. Use the energy diagram to answer the questions that follow. And if, like I said, tomorrow is a work day, there is another paper to analyze that you guys don't have on your packet. If you are confused as to how to read one of these diagrams, that is what tomorrow is for, because there's not much to do in the thermodynamics unit. It's this one, and it's the one on Thursday, and that's it. So the activation energy of the reaction is about how much? Okay, so since I can actually write on my board for a change, the activation energy, no, this is not right. The heat of the reaction, the activation energy is not right. Let's see if you guys can tell me what I did wrong. So my activation energy, my potential, and we're going to fix this. My potential is 240, but my activation energy is here. I'll fix this. This is what happens when I'm doing this last second. What's 240 minus 80?
160.
Okay. I'm going to change that here in just a second. To be able to change from reactants to start making products. So let me fix this real quick. I hate when I catch typos like this. This is actually 160. It requires the energy to do that, which is why it's positive. Come on. Why are you doing this? I broke it. There we go. Now the heat of reaction, which is the difference. Oh, shoot. Here, I'll use a different color. My heat of reaction is 160 minus 80, which is 80. That's where I got that from. This is my delta H. That's my enthalpy, or my heat that's required to do this. Oh, I gotta put my pen down. I'm just excited I can write. Now, this reaction, bigger hump going up is endothermic, like roller coaster. More distance going up is endothermic. More distance going down is exothermic. So this is an endothermic reaction, which means my delta H is a positive 80 kilojoules. So now the other things, because you have to be able to do this tomorrow, my potential energy, this is not on your paper. My potential energy of my reactants is 80. My potential energy of my products is 160. My potential energy of my activated complex is 240, and that was the typo that I had up here because I honestly did not make these notes until yesterday because I have been so slammed with life right now. Now, I know we only have 5 minutes. Let me stop the recording.